Shall we start? Good morning. Today we want to talk about quantum error correction. And contrary to the previous days in which I talked about classical things in the morning and quantum things in the afternoon, today I will talk about quantum about in the morning lecture and in the afternoon. But I do not insist to be complete and to finish the lectures, depending on how much we interact with each other. We'll go through these slides and then see what happens. Okay? So please ask questions. Please interrupt me if anything is obscure or incomplete, or please object to whatever that you do not like, or you do not find it. Okay. Why quantum errors are so serious? In fact, they are very bad. They can destroy all computations. There was a time that people thought that also all these quantum algorithms are fascinating, are very powerful, and can solve extremely hard problems in short terms. Also, they can solve problems that classical computers cannot solve in millions of years. Also, all these capabilities are in the quantum computers. Nevertheless, quantum computers are useless. They cannot be built because there are errors. Of course, in classical computation, there are also errors. But the errors in classical computation are quite easy to solve, to detect, and to correct. But the quantum errors are extremely bad. We want to see why. Right? Classical bits have 4 basic good properties. Right? These are the bits. One of them is 0, the other one is 1. These are classical bits. And why? They have good characteristics. The first one is that bits are macroscopic objects. They are not macroscopic of the size. On the atomic level, they are macroscopic. Any classical bit in your computer, in your phone, in your iPad, in your laptop, anything, consists of a macroscopic object of thousands and millions and billions of atoms form a single bit, right? A magnetic domain on a hard disk forms a bit, a classical, but that magnetic domain consists of billions of atoms, right? If the atoms and the spins and the magnetic moment of the spins of the atoms point in the up direction, the bit is 0. If they point in the down direction, the bit is 1. Now, if in these millions of atoms, 2 atoms point in wrong direction, 3 atoms point in the wrong direction, even thousands point in the right direction, or wander around, it doesn't matter. 1 is still 1. 0 is still 0. So these are macroscopic objects on the atomic level, and they are resistant. They are not destroyed in the computation. Okay? This is the first problem. So this is the case that we have a 0 bit. As you see, the majority of them are in the up direction, but not exactly in the up direction. Some of them are tilted, but it doesn't care. The other one is bit equal to 1. Some of them may even be up, like this one. Right? But the whole thing represents a bit which is equal to 1. Right? This is the first part. Then, Angelo showed us that quantum states cannot be cloned. We do not have a copying machine on the quantum level. But on the macroscopic, the classical, the bits, they can be cloned. You can copy a 0 bit to 3 bits, or 5 bits, whatever that you want. So you can prevent errors. You can copy the information that you want as many times as you want. To prevent errors. If you want to say to say hello, and there is a probability of error, you say hello 3 times. Right? Or you say hello 5 times. Then everything is okay. So classical bits can be cloned, but quantum bits cannot be cloned. That's the second basic good property of classical bits. And then the third property. Classical errors are discrete. So the error means that 0 becomes 1, and 1 becomes 0. This is the classical error, right? There is no other error. 0 doesn't become 0.95. The error means that 0 becomes 1, or 1 becomes 0, right? This is the third property, good property. And the fourth property. Bits can be observed. You can observe a bit to see if it's correct or not. Right? Do you agree? You can observe a bit because it's a classical object. It's not disturbed by your observation. It's not disturbed. It doesn't collapse because it's not in a superposition. So you just observe the bits to see if they are true or not. If they are true, if they are correct, you leave them. If they are not, you correct. So these are the 4 basic properties. Do you agree? Exactly. So we have 4 basic good properties. Let me repeat. They are macroscopic. The errors are discrete. They can be copied as many times as you like, and they can be observed to detect it. The quantum bits have exactly the opposite properties. Right? So by just seeing this, you will be disappointed at quantum computation. People really were disappointed. They thought that quantum computation is completely impossible due to these errors. Why? First of all, quantum bits are microscopic. A quantum bit is an atom, is a photon, an electron, and a quantum dot. Right? It's not microscopic. So it's very delicate, extremely delicate, extremely fragile. The quantum bit can be destroyed even when a photon passes by. It can flip. Right? It can lose all the superposition and the information, etc. Right? That's why the question that one of you were asking yesterday, that maybe there will be some time that we will have a quantum computer in our pocket. Maybe, but it will be very difficult to maintain. We have to think about the error correction in that case. Anyhow, they are microscopic objects. The second one, they cannot be cloned. You cannot repeat a state. To prepare psi from one side. You cannot repeat. The information is just on this side. You cannot clone it because of the theorem that we saw just now. The third property is that they are continuous. Bits are zeros and ones, classical bits. But quantum bits are states, like this one. And then it gradually may change. We wander around, right? You start from this state, and gradually it becomes this state. It becomes this state, right? It's not a discrete error. It's continuous, right? So A 0 plus B1, because of this superposition, becomes A prime 0 plus B prime 0, B prime 1. And as you do more and more computation, it changes outside of your counter, right? And then the fourth property is that they cannot be observed. You cannot observe quantum wave to see if it's correct or not. The moment that you observe, it collapses and it loses all the superposition, which was the main strong property of quantum wave, of quantum computers. We saw that the main power of quantum computation comes from superposition, this exponential power. And now the errors are such that if you continue to correct the errors, immediately the state collapses and loses all this superposition and all the information which is inside the superposition. So, what do you suggest? Shall we do quantum computation or not? Is there any hope that we can correct quantum errors? It's much better that we think and go through all these slides. Is there any hope? Who wants to do quantum computation? Who has any hope?
We have to figure out to build some quantum logic gates to do these corrections.
Yes, that's a good, very good idea, but that quantum logic gate should operate on qubits, and the input may have some errors, and the logic gate may also have some errors, right? In the same way that we will explain. So we have to do it, you are correct in the sense we have to do it in a very dedicated way, right? We have to do it in a very dedicated way. Let's see how. First of all, let's see how classical error correction is done. Classical error correction is done by adding some redundancy, by some cloning, or better to say, to add some redundancy. For example, instead of 1, 0, right, we store this 0 in 3 bits. You repeat, you clone. And instead of 1, you clone it and store this 1 in 3 bits. What is the philosophy of this? The philosophy is that you separate these 2 bits, right? And around them, there are 2 spheres. The distance between these 2 encoded qubits is large enough, so that any error, 1-bit error, from 0 to 1, the encoded, or 1 to 0, is highly improbable. In fact, let me write here. This is my initial 0, but I encode it in these 3 zeros. I encode 1 into 3, 1, right? And then if I store this 3 bits in my computer, and tomorrow come and see that it's something like this, I'm talking about classical, so I can observe. If I see something like this, I say that, okay, this 1 has been this 0, which has been flipped, right? So I correct it. I correct it to 0, to 0, 0, 0. If I only see this, something like this, right? If I see something like this, by the majority rule, I say that this has been this bit, and I correct it. But I'm doing a mistake, because 2 bits have been flipped here, right? But this is highly improbable. What is the probability of my mistake? The probability is that 2 bits flip or 3 bits flip. The probability of 3 bits error is this one. So this is the probability of, this is the probability of all 3 bits to be flipped, p to the power 3, because p is the probability of 1 flip. And how about this? This is the probability of 2 flips. P squared times 1 minus p. What is 1 minus p?
The rest of the probability.
Exactly, the probability of not being flipped. And what about this 3? How about this?
Diameter.
Sorry? Yes?
Location of two.
Yes, location of the bit flips. So, this is the probability of this new encoding, which is almost 3p squared. So by this encoding, by this separation of bits from each other, right, by this distance, I have lowered the probability of error from p to 3p squared. And p, remember that p is very small. In classical computers of today, p is the order of 10 to the minus 7. So I bring it to 10 to the minus 14. It's almost zero, right? This is the philosophy of classical error correction. You separate the bits from each other so that they do not overlap with each other, right? Now we want to go and find one simple quantum error correcting code. And we want to see how all those 4 obstacles can be removed. We have 4 very strong, very bad obstacles. First of all, some notations. You know all the Pauli operators. In quantum computation, the notation sigma x, sigma y, sigma z is not usually used, right? You just use x, y, z, capital X, capital Y, capital Z. So this is the operator z, you all know it. It's diagonal 1 minus 1. This is the bit 0, which is spin up, so to say. This is bit 1, qubit 1, which is spin down. And 0 and 1 are eigenstates of z, with eigenvalues 1 and minus 1. Right? These are obvious. Okay? And this is the sigma x operator. And we call it a flip operator, or bit flip operator. What does it do? It flips 0 to 1 and 1 to 0. Right? This is the 0, and the x operator flips it to 1. And the x operator flips 1 to 0. So this is it's called bit flip. The first thing is that quantum errors are really not continuous. Contrary to our initial understanding, quantum errors are not continuous. It's the probability that is continuous. Right? The errors are always I, which is no error, x, y, or z. Why? Because if you consider a qubit and its environment, any operator, any big unitary operator, which acts on this qubit and its environment, can be written like this. You expand omega, which is the big unitary operator, in terms of the basis of sigma Pauli operators on the first qubit, on the qubit, which are I, X, Y, and Z. You know that the operators I, X, Y, and Z are the basis of operators in two-dimensional Hilbert space. Every operator can be written in terms of this. So you write the omega, which is the big Hilbert unitary operator, in terms of this basis. And you call the rest U0, whatever it is, U1, U2, and U3. This is the operator which acts on the whole space, the qubit and its surrounding. And then what happens? All the continuous parameters, goes to this U0, U1, U2, and U3. And here you see that the operators which are acting on the qubit are I, X, Y, and Z. All the parameters which were continuous goes to these operators U0, U1, U2, U3. And they are acting on the environment, and effectively they act as the probability of this error. The probability of a no error is determined by U0. The probability of an X error is determined by U1. The probability of Y error is determined by U2, etc., etc. That's the first one, the first insight. This is again an explanation of this. Psi is the state of the qubit. E is the state of environment. We do not know the environment. This is the operator which acts on both of these. And I expand this omega in terms of the operators which are acting here. I, X, Y, and Z. U0, U1, U2, and U3 act on this environment. Right? So, on the qubit, you will not see any continuous, the discrete errors are X, Y, and Z. And X, Y, and Z, we know from the Pauli operators, they do not contain any continuous errors. Continuous parameters. Any point? Questions? No? So, in effect, omega times psi times E becomes something like this. Psi times E0, E0 is the state of the environment. X psi times E1, E1 is the state of the environment. E2 and E3, right? Now, if I keep my qubit state as a one qubit state, as psi, right? As state as this one, I have one qubit state, A0 plus 1. Suppose that my argument in the previous page works. The errors that are happening on this qubit are Z, X, and Y, because I is not. You agree? I is. If an error like Z happens, then the state becomes A0 minus E. You agree? You agree? How about this one? X flips 0 to 1 and 1 to 0. You agree? And the Y, A1 plus I is 0, because Y has an I. Can I understand, can I detect which of these errors has happened? Can I understand? Can I differentiate this state from this state from this state? Who says yes? Can I do some kind of measurement and understand which of these errors has happened? Because I want to detect the error. I want first to see what kind of error has happened before correction. We have to detect it. We leave it to the both of you. Can we understand and detect the error now? Look at these states. Sorry? Can you conceive of any measurement? Suppose that you do a Z measurement in the basis of 0 and 1, right? And then we want to see if you have this top state or the bottom state or the middle state. What is the probability of finding 0? A squared. The probability of finding 1, B squared. What about the other one? This one.
B squared and B squared.
A squared and B squared. This one, A squared and B squared. Right? So you do not understand which of these errors has happened. Because the probability is the same, almost the same. You just have the statistics, which doesn't enable you to understand which of these errors has happened. You agree? This is simple quantum mechanics. Right? Because all these states have overlapped each other. Right? And we have one copy of this. Even if we had a copying machine, cloning machine, even if we have, Then, these states are not orthogonal to each other. So we could not copy them and understand which of these states we are dealing with, because they are not orthogonal to each other. So what should we do? We should encode in such a way, we should encode these qubits in the same way that we did in the classical machine. We encoded 1 0 to 3 zeros, 1 1 to 3. We should encode our qubit to a number of qubits, perhaps 3, perhaps 4, I don't know, so that when an error happens, the state which is living in my quantum computer, so it goes to different orthogonal subspaces. So an X error takes this space to this, takes this Y to here, takes this Z to here, and they completely should be orthogonal to each other, right? They shouldn't have any overlap, so that I can make a measurement. And by taking the measurement, by making the measurement, I understand, I am in this subspace, am I in this subspace, or this one, or this one? Without understanding the state itself, I just want to understand the error. If I find that I'm in this space, what should I do to correct this state? I just act on the state by an X operator, because X squared is 1. The polynomial X squared is 1. Right? Y squared is 1. Z squared is 1. So if I find that I'm in this space, right, I act on the state by an X operator and come back to the state. The same goes for here and here. The point is that by this strategy, I should not be able to find the state itself. Because finding the state itself means that you ruin the state. You destroy the superposition. You destroy the information. You should only understand the error itself, whether it is X, Y, Z, or 1. Clear? Is it clear? Any question? Question? Yeah. Yes,
So
please.
for each qubit, we are going to design 3 more qubits.
Yes.
For tapping that errors.
Yes, exactly. We should use more qubits. With 1 qubit, you cannot use. You should encode. It's all the problem of encoding 1 qubit to many more qubits, so that this is possible. Right? You have to spend it, like in the classical case. But
In classical, it's inverse of this. Like here we are copying the error, like making error type qubits in order to pull the error one to its own side. But in classical, like we are using a true or a correct bit, like copying the correct bits.
no, it's exactly like, not exactly, it's similar to the classical case. In the classical case, you encode 0 to 3 zeros, do some encoding, and 1 to 3 1. There are more complicated encoding than this, in the classical domains even. But this is simple. Now you encode 1 qubit to 3 qubits, maybe. But we will see that this is not the case. We need more qubits. Or encode 1 qubit to 3 qubits, but not in a simple way as this one. We will see it's more complicated, because we are dealing with quantum computation. Right? So we have to spend some more qubits. It doesn't come for free. Error-free quantum computation doesn't come for free. You have to spend qubits. That's why doing real quantum computation is extremely difficult. People have to use lots of quantum bits. It's estimated that the present day cryptographic system, which is classical, will be broken by quantum computers, by the short code, right? Then you can arrange 20 million qubits. 20 million qubits. Note that the IBM quantum computer and the Google quantum computer have only 100 qubits. In order to break the cryptographic system of today, to implement the shortcode, exactly due to this difficulty, error correction, you have to assemble 20 million qubits, right? But do not be afraid. We will not go to 20 million qubits, we just go to a small number of qubits. But that's the perspective. So, we agree that we should go to different subspaces, orthogonal subspaces. So, the simplest example, okay? I encode a qubit 0 state. This is not a state, it's not a classical case. To this state, to 0, 0, and 1 to 1, right? This is the simplest code that I use. Now, in the quantum computer, the qubit has a superposition. So my state is not just 0 or 1. It's A0 plus B1. And it's encoded into A00 plus B11. This is my encoding. Right? Okay? Now let's see what happens. So this is my encoding. Psi is the initial qubit. Psi bar is the encoding qubit. I use it to detect and correct the errors. Okay? Sure? Let's see what happens. Now the original state, first of all, now I'm only concerned about the bit field. Okay? Any error correcting codes can deal with a certain number of errors, not all errors in the world, the most common errors. Now suppose that we restrict ourselves only to qubit errors, to bit field errors, to the X errors. Okay? Here is my initial state, A00 plus B0. If an X1 error happens, it means that if the qubit 1 undergoes an error, so the bit flip 1, number 1 flips, this state becomes this state, A10 plus B0. Do you agree? Do you agree? Right? If the second bit flip occurs, then A00 becomes A01, the second bit now flips. And B11 becomes B10. Right? Now, this state is orthogonal to this state. Anybody agrees? Anybody disagree? This state is orthogonal to this state. Do you agree? Do you agree? These two states are orthogonal. How about these two? They do not have any common state. They are orthogonal to each other. Right? So I can understand whether the error has happened or not. I can differentiate these two subspaces from this subspace. They are orthogonal to each other. I can understand. Do you agree? You do not agree. Now let's see. The original state is this one. That's B1. Right? It has become this state. Psi prime, call it psi prime, which is A10 plus B01. Right? Now I calculate the inner product of psi and psi prime. What got them? Right? This state is orthogonal to this state. Because we have here 1, 0, here we have 0, 0. They are two different states. This state is orthogonal to this state. This is orthogonal to this state. They are all different. So you obtain 0. They are orthogonal to each other. When they are orthogonal, it means that you can differentiate them by some kind of measure. Right? In the same way, this state is also differentiable from this. So I can understand it by some kind of measurement. Anybody disagrees? Any objection? This error correction is a delicate subject, so we have to be patient. No question for you. Can I understand whether x1 has happened or x2? Can I understand? Please speak loudly. Can I understand x1 has happened or x2? Yes, to the first key. Can we understand? Can we differentiate? I want to understand whether x1 has happened or x2 has happened. Are you sure? Are these two states orthogonal to each other? Orthogonal? These two states. No, they are not. Right? They are overlap. So there is no measurement which I can perform to see whether x1 has happened or x2. And if I cannot determine which error has happened, I cannot correct it. Suppose that I just say by chance that this error has happened. Right? x1 has happened. Then, by chance, I say that x2 has happened. Then, I act by x1 and x2. Because this is the error that has happened. Then I act by x1. x1, x2 is opposite to 1. And I do not obtain the original state. I obtain something else. Right? So in order to make an error correction, you have to differentiate exactly which error has happened. Here is technically called an error detecting. You understand that an error has happened, right? Because these two states, these two subspaces are orthogonal to each other. These are also orthogonal to each other. But you do not understand which error, so you cannot correct it. You can just detect it. So do this, right? In order to detect an error and be able to correct it, you have to spend more. Remember again that we are talking only about beta. Okay? Any objection, question, comment? Okay. Hey. So let's, before going to error correction, suppose that we want to see if an error has been occurred or not just for correction. How do I understand that an error has occurred? How do I understand that I am in this subspace or in this subspace? Right? We agree that we can understand that if an error has happened. This is very delicate and the heart of the error correction scheme. Let me explain. Can I use some water here? Is it possible? So, z over z is equal to 0. You agree? Z over 1 is equal to minus 1. Okay? Now I want to understand whether I am in this subspace or in this subspace. Right? I want to make a measurement. I want to make a measurement without destroying the state. Right? Without destroying the state. If I measure the state, first state. If I measure this, the first state, what happens? The state immediately collapses with a 0 or 1, right? It immediately collapses. I have to make a measurement to understand whether I'm in this subspace or in this subspace, without destroying the state, without destroying the superposition. And that requires a clever measurement. The point is that if I act by Z1, Z2, this is my observable, right? Over 0, 0. Right? Z1 acts on this one, Z2 acts on the second one. Because you have two plus signs, you obtain 0, 0. Right? Z1, Z2 over 1, 1. What do you obtain? Plus sign or minus sign? Plus or minus? Plus, you obtain 1. So Z1, Z2 and Z1, Z2 over 0, 0 and 1, 1, they have the same eigenvalue. It means that this state is the eigenvalue of Z1, Z2 with the eigenvalue 1. Because both states have the same eigenvalue. So if you act on Z1, Z2, if you observe Z1, Z2, and you measure Z1, Z2, on this, it doesn't collapse. Right? Because it's an eigenstate of Z1, Z2, with eigenvalue 1. What do you obtain if you measure Z1, Z2 on this state? What do you obtain? Both of them are eigenvectors of Z1, Z2. What eigenvalue? 1 or minus 1? Minus 1. Both of them. So you can measure Z1, Z2 on that state. And that state is an eigenvector of Z1, Z2. It doesn't collapse. So you just measure this observable and understand whether an error has happened or not. If you obtain 1 without destroying the state, without collapsing the state, you say that I am in the right subspace, in the original subspace. If you obtain minus 1, you say that an error has happened. Right? Z1, Z2 is the symptom or syndrome of the error. Right? How about this one? What are the eigenvalues of Z1, Z2 for this one? Again, minus 1. That's why I do not understand which of these two errors has happened, because they have the same symptom. They have the same symptom of the illness. Right? I understand that my patient, which is this qubit, encoded qubit, is something wrong with it. I understand the symptom. It's minus 1 here, it's minus 1 also. I do not know what is the exact illness of this qubit. I know that something is wrong. Right? My patient or my qubit is not doing right. I do not understand which illness it is. Right? For this, I have to spend a little more. And the point is that I should do this. Okay, this is the repetition of what I wrote on the blackboard. This is the original state. This is the error. And this is the symptom. Z1, Z2 has the eigenvalue minus 1 for this whole subspace. For this whole subspace equals minus 1 for this as well. So this is an error detecting code. Not error correcting code. A better code is this one. You have to use 3 qubits. You encode 0 to 3, 0 and 1 to 3. And any state like this one is encoded to A double triple 0 plus B triple 1. Right? Now what happens? Now, this is my original state. If an x1 happens and the first flips, this state becomes this one. Do you agree? Yes? If the second qubit flips, this state becomes this one. Right? The third one flips, this state becomes this one. You agree? Is this subspace or state orthogonal to this one? Do they have anything in common? Do they have anything in common? How about these two? Any state in common? How about these two? So I can detect it. How about these two? Do they have anything in common? How about these two? These two. They do not have anything in common. So I can understand in which subspace I am. Whether x1 has occurred, x2 or x3. Right? You agree with this? Right? So in principle, it's possible to determine which error has occurred, in which subspace I am. Now, instead of Z1 and Z2, which were the symptom for the previous encoding, you have to use a more delicate symptom to understand in which subspace you are. Okay? What are the symptoms that you propose? Propose a measurement that I do so that I can understand in which subspace I am. What is next? Propose a measurement without destroying the superposition. Yes?
Creating error qubits as we did before for the previous slides.
Mm-hmm.
Creating 3 more qubits. If our qubit, which is supposed to be getting into error, could we go to that error qubit?
Mm-hmm. You are approaching the correct answer. Now we have 3, right? Z1, Z2 on this becomes 0, 0, 0. You agree? And on this, it becomes 1, 1, 1. Right? But besides Z1, Z2, Z2, Z3 determines whether the bit number 2 and number 3 are the same or not. Right? So you have 2 symptoms. Z2, Z3 are on this state, again becomes 0, 0, Z2, Z3, and 1, 1, 1 is again 1, 1, 1. So you have 2 symptoms. One symptom, which is Z1, Z2, determines whether the first 2 qubits are the same or not. Z2, Z3 determines whether the second pair are the same or not. So by these 2 kinds of measurements, which do not destroy the superposition, which do not collapse the state, you can determine in which state you are, in which space you are. Let's see how. These are the symptoms, and these are the errors, right? These are the symptoms, the measurement, and these are the errors that has happened. There are 4. I is a node. X1, the bit flip error on the first qubit, X2 and X3. And these are the symptoms. And as you see, all the symptoms are different. And they do not destroy the state. Because all these states are subspace, are eigenvectors of these 2 operators. When you measure these 2 operators, the state doesn't collapse. You just look at the eigenvalues, look at the lamps on this subspace to see if the lamps are 1 or -1, green or red. Right? This is the original state which has eigenvalues 1, 1. It's a correct state. This is the eigenvalue -1, 1. Why -1, 1? Let's see. The first 2 qubits are different. But the second pair of qubits are the same, right? 1, 1 and 0. That's why the symptom is -1. How about this one? The first 2 qubits are the same. So you have this one. The second pair are different, so you have -1. And this one, you have -1 and -1. So you measure these two operators, you measure these two observables. The state doesn't collapse, but you understand that in which state you are. So in this state, in this clever measurement, we could bypass that great obstacle of quantum computation. We can observe something, we can detect the error, right? Without destroying the state. That was a big, big obstacle, that you cannot observe anything, you cannot detect anything. Detect it. The moment that you detect, you destroy the state. Now we can detect the error without destroying the state. It's a really ingenious way of detecting. Right? Are you happy with this? Are you happy? Why your face doesn't show that you're happy? Maybe it's an inside happiness, right? A spiritual happiness. Any question?
Can I ask you?
Yes, please.
I don't know if it's this situation. Is it always the case that when one flip happens, both of the qubits flip?
No, X1 only flips one qubit, the first qubit.
The state with the probability with B and A, they both flip, right?
I see.
Is there any case that only one of the
Yes,
states?
it's a very good question. It's a very good question. Maybe both qubits flip, right? Then I cannot detect that, right? But the probability of both flip is small compared to the probability of one flip. It isn't the case in any kind of error correction. Probability of one flip is P, for example. The probability of two flips is P squared, which is low. The probability of three flips is P above Q, which is still low. So we have always to trust that our computer is doing bad, but not too bad, right?
So we are ignoring.
Yes, we are ignoring it. And then, any kind of error correction scheme, whether in the classical or in the quantum domain, can correct only a certain set of errors. Those errors which are the most probable. If you want to correct the errors, double flip errors, you have to spend more, right? To make a longer code, right? This is not peculiar to quantum mechanics. Even in classical domain, this is the case. For example, in this very simple repetition code in the classical domain, right? If both flips occur, you cannot detect it. You may make a mistake, right? Because your majority rule will disappear. Any other questions? This is a very good point. Okay, so these are the errors and these are the symptoms. Am I beyond the time? Finished?
It's over.
Okay. So, I promise you that I will not go to the end of the lecture, and this is the point where we can stop. We learn how to detect the big flip errors, right? But there will be some other type of errors, the phase flip or some other phase. Why? We will see in the afternoon how we can detect those errors separately and how we can detect and correct all the errors so that we have a safe quantum computer, right? So we stop here and continue in the afternoon. Thank you.